So I'm John Reppy. I'm going to talk about this work that Dave has written up, and it's his work. It's not my work. So just to give you a little bit of background and a little bit of advertisement, because sometimes I think people think that Standard ML New Jersey is dead, but we're not dead. We're still going. And over the past few years, we've been putting a lot of time into eliminating technical debt by overhauling large parts of our system. And so for some examples, in 2019, we finally got around to implementing 64-bit support. Toward the end of last year, we released a version that now uses LLVM as our code generator. And there was a paper in IFL 2020 that describes that in much more detail. This summer, I spent my time migrating stuff to GitHub, which actually sounds like it ought to be simple and quick, but it turned out to actually take a lot of time, mostly because we wanted to migrate our bug lists and stuff like that. And this paper is another piece of that general modernization effort, which is about the re-implementation of the match compiler and the SML New Jersey system. And just to give you a little bit of history here, so the match compiler that we have was written by a summer intern, Bill Aiken, back in 1992, I think it was. I think I'm remembering correctly. I was fresh out of graduate school at that point, and was his supervisor, but he really did all the work. And then it got some overhaul by Zhang Shao and his students when they put in the Flint intermediate representation and various other things. But it really has basically been unchanged for about 30 years. So there are a lot of different ways you can implement pattern matching. The simplest thing you could do is you could directly interpret, which is what I believe Hamlet does, and Andreas can correct me if I'm wrong, but essentially you can look at the semantics of pattern matching and iteratively go through each rule in the case and try to match it. You can also compile to a backtracking-based implementation. So this is a little bit more complicated, but it allows you to eliminate some of the redundancy. And if you are ambitious and use the results of this paper, you can actually eliminate a lot of redundancy through fairly complicated but clever techniques. Another approach, which is sort of the one that Standard ML New Jersey has followed, is decision trees. And there are a couple of different ways in the literature to compile to decision trees. So the most common one, I think, is the use of pattern matrices. So essentially, you can imagine the case expression represents a matrix of patterns, and then as you do things like untuple stuff, you add rows, and as you do matches on columns, matches on constructors, you eliminate columns, and eventually you get down to a base case. Peterson's dissertation is a very nice description of that approach, but there are others out there. Or you can use an intermediate data structure, which is called an and/or tree. So the idea is that data structure sort of captures information about the case expression, and then you use that to construct a decision tree. And that was originally described in a unpublished paper by Baudonnet and MacQueen back in 1985. This paper gets a lot of citations, but wasn't published, and that's what this talk is going to be about. So the and/or tree approach is what Standard ML of New Jersey has always used in its implementation. So the algorithm has a fairly simple structure. It's got, roughly speaking, 3 passes. So the first step is to convert the case expression into an and/or tree. And this is done by basically iterating over the rules of the case. And for each rule, we layer that rule over the existing tree and add additional information. Then once we have the and/or tree, we can extract a decision tree from that. So the decision tree basically is just the conditional control flow that we're going to use to implement the match. And that's basically done through a kind of recursive work list algorithm. And the key thing about this work list is that it's an ordered list, and the choice of ordering that you use determines, in some sense, what the shape of the decision tree will be. So by tweaking that ordering, you can change the shape of the tree. You can make, get bushier trees or deeper trees or things of that sort. And then the last step is that you take the decision tree and you convert it into some internal representation that the compiler is happy with, such as abstract syntax, and that flows through the rest of the compiler and get some code out at the end. So I'm going to go through basically some examples. First, I'll tell you a little bit more about AND/OR trees, and then I'll go through some examples to illustrate these steps. Again, the paper has more detail, and the code, source code, of course, has all the detail. So an AND/OR tree is basically a data structure that summarizes the rules of a case expression. And it consists of, as you would expect, AND nodes. So AND nodes represent tuples in the patterns or labeled records. And we're going to draw these this way with labels on the outgoing edges that represent the position of the component corresponding to that subtree. So number 1, number 2, or #1, #2, #3, standard ML syntax for projection functions from a triple. It also has OR nodes. And OR nodes are the choices between constructors. OR nodes also can be used to represent the choice between primitive types such as strings, integers, etc. And these have outgoing edges that are labeled by the value by the constructor value that represents that choice. So an OR node on a Boolean might have a true child and a false child. But an OR node doesn't actually have to have a child for every single value or constructor value that it's testing. In particular, here we might have an OR node which just has a single child labeled true. And the general idea here is that we're only going to add edges or children to OR nodes when there's a corresponding constructor in the pattern for that child. So if there was only a true but no false in our pattern, then we're going to get an OR node like this. We also have terminal leaves, which are basically the children of null array constructors, and I'll write those as bottom. And we have unexpanded leaves for variables and wildcards. And the variable story, as usually is with pattern matching, actually has additional technical wrinkles having to do with bindings, as patterns, etc. I'm not going to talk about those. In fact, I'm going to just restrict myself for the rest of the talk to patterns that just have wildcards in them. Okay, so I guess the last piece. So the other thing is there's additional metadata that we attach to the nodes in an AND/OR tree, and some of this is things like type information, but the most important from the point of view of this talk is we remember the live rules, and by live rules, these are the rules that are affected by each of the, these are the rules that the node actually has some control over. So that will, I hope, come clear in the example. All right, so I'm going to start with building an AND/OR tree for this small case. So we have 3 cases. The X has the type Boolean bool list, and paired with bool list. And you'll notice, by the way, that this is not a exhaustive match. So we start with a question mark because we don't know what X is, and we haven't looked at any cases. And we'll look at the first rule. Now, the first rule tells us, well, we're dealing with a pair. So we're going to have an AND node at the root because it's a pair. We have to deconstruct that pair first thing. And then we have a true and a nil. So those are going to give us OR nodes. And we have a true child, right? Nil child. So then we do the second rule. Now the second rule has a wildcard in the first position. So that's not going to add any structure over here, although we do record the fact that this OR node is live, but we are going to get structure over here. And that, again, because cons takes a pair, we get an AND node, and then the head of the AND node is true, so we get an OR node going to true. Here we have a wildcard, so we just get a question mark. And then we do the third rule, and that adds a false edge down here to the OR node. And that's the tree that the AND OR tree we get for this particular example. Okay. Sorry, I lost my clock. Okay. All right. So once we have the AND OR tree, we can build decision tree. And the key idea of the decision tree is that we're going to keep track of a frontier of OR nodes, and these represent the possible decisions that we could make. And it's a choice of an OR node from that frontier that governs the shape of the resulting tree, because there are many different decision trees you can get out of a given case. So to start with, we get two OR nodes, and I've added subscripts to these OR nodes just to allow us to distinguish between the ones in the between the two different OR nodes, or three different OR nodes. So we start off, we have these two OR nodes. Those are the ones that are reachable from the root. And I'm just going to pick the second one. And that gives me an initial decision tree. We have at the root, we have an OR test. And the possible results are either cons or nil. So those are subtrees that we're going to have to expand out. Now, I'm going to pick expanding out the cons first. So I'm going down here. And that causes my frontier to change. So now OR1 and OR3 are in my frontier. And I'm going to just arbitrarily pick OR1 as the thing to expand next. So that gives me an OR node here. And I'm going to have, because it's a Boolean, I have to worry about true and false as the two cases. I go down the true branch and compute a new frontier. Now, oh, sorry, I should maybe go back for a second. So when I go down the true branch, OR3 is still in my frontier, right? I have not resolved that. So I have to pick that one. That's going to give me true and false. So in the case of true, I'll end up at 2. In the case of false, I'll end up at 3. And now I have an empty frontier, but I still, so I sort of back up to here. So I still have my OR1 that I'm trying to resolve, but OR1 has no outgoing edge for false, right? So there's no way to expand that node because there's no outgoing edge, and therefore I end up with a match failure, right? And so I just put in a fail node in my AND OR tree. And now I can go back up to this OR2 and deal with the nil case. So going down to nil, that doesn't tell us anything. But we still have OR1, so we can expand OR1 out. And that, as before, we get true and false. And then we can, as before, as we did down here, we can expand those edges out and we get 1 in the true case and fail in the false case. And so that's the base. I hope gives you a sort of intuition about how this algorithm works. It's fairly straightforward, but the main challenges are basically keeping track of the frontier. But the key thing here is that the ordering on the frontier is a place where you can introduce heuristics for how you want to actually choose which decision to make next, and that's is a useful tuning parameter for doing this. And Norman Ramsey many years ago wrote a very nice paper that described, sort of did a very exhaustive survey and performance study of a lot of different heuristics. So I believe that that's referenced from Dave's paper, so you can go take a look at that if you're interested. Okay, so then the last step is constructing abstract syntax. So just to remind you, this is was our initial program. This is our decision tree, and we end up with something that's going to look like this. Here, what I've done is I've just written cases that are simple cases, so they just involve either just a single constructor applied to a single argument, and then we're just doing projection to extract the components of the tuple. And so if you throw variables into the mix, then things get a little bit more complicated because you have to make sure you get the right bindings and everything. But in the non-variable case, this is very straightforward. Okay, so I'm not sure where I am on time, but just at 15 minutes. Okay, great. So, in conclusion, more technical details in the paper. The main, so this approach, as I mentioned before, has been used basically since the beginning of time, as far as we're concerned, which is almost 40 years ago. The world started, yeah. Well, no, that's in New Jersey. Because of course there was a pre-con when you had like Edinburgh, stuff like that. The key advantage of and/or trees as an approach is really this fact that OR nodes are that you have this frontier of OR nodes and you can choose among them using any choice is going to be correct, and so you have a chance to tune how you construct decision trees. This implementation is in our current development branch. We've actually bifurcated into a sort of a legacy branch, which has like 32-bit support and things like that, and then a development branch, which is more bleeding edge. So it shipped last December in 2021.1, and it's also in a more recent release, 22.1. And Dave is working on a long version of the paper that has a lot more technical detail about the algorithm and whatnot. And when he finishes, we'll post that on our GitHub project. So thank you.